Continuing on with our discussion about beam design and deflection, this is another problem that I wanted to show you, and kind of keep in mind that we got to make some assumptions. And to continue, I looked up some values earlier on, and hopefully this will help you see where the numbers came from and give us some good ideas on how to evaluate these problems and do a good job of sizing the beams and looking at cost and schedule and assorted other factors. But let's get rolling. Again, I've drawn a beam here. It's 12 feet long, and our total load per foot is 100 pounds. You'll notice it says the W, and that is 100 pounds per lineal foot. You notice also at the top, and I'll star right here, you will notice that these guys are spaced at 24 inches. I've looked up some approximate values for bending stress is 1250 psi. Our allowable horizontal shear stress is 95 psi. We're going to use a modulus of 1.7 times 10 to the 6th psi. And you notice a new value, the RF, which is a repetitive member factor, and we'll talk about where that plays into our calculations momentarily. But again, recall that we're going to look at bending stress, and we are going to look at shear stress, and we're going to look at deflection to make sure that the beam that we select will work for the design loads we've given it. And also notice right up here at the very top, we have the given, or I should say the fine component of our problem is to determine the depth of a 2x member that will tolerate these loads. So we're going to go through this problem step by step, and I've made an assumption. If you'll notice right here, we're going to assume obviously a 2x, but we're going to look at something we're almost sure from experience that it'll be 5 inches. I use the phrase wider, but that implies a deeper section. So let's kind of take a look at how we're going to solve this thing. Now again, recall from our classroom work that we need the shear moment diagrams. Well, we have equations, but we also, let's take a quick look at how to get the reactions and maximum shear stress, or I should say maximum shears and bending values. I'm just going to draw some lines down here so we can progress as we did in the course or in the other classroom problems that were similar to this. Let's take a look at our shear diagram. And if you recall, at 100 pounds per foot, our total load is going to be 1,200 pounds, and it's going to act right there. So that is 1,200 pounds. And recall, this is a rectangle, so that is going to act in the center of our section, so that is at 6 feet from the left and or the right reactions. You'll also recall that given that, I'm going to have a left-hand reaction of 600 pounds here, and given that it's symmetrically loaded, we will have 600 pounds over here. You'll also notice, if you'll recall from our discussion, that our shear equation or our shear diagram is going to look something like this. And it's a little off, but that'll be okay. This number here is 600. We notice that this reaction over here is 600 as well. But we also recall that the slope of this line is 100x, because it is 100 pounds per foot. Well, let's quickly sketch the moment diagram. Please watch the color, and we know that it's going to look something like this. All right? Now, again, it's a little off, but we want to know something about the value right at the top of there, so we know that the maximum shear value from this guy is 600 pounds. So Vmax is equal to 600 pounds. And recalling, if we integrate the load, we get the shear, and when we integrate the shear, we get the moment. Well, we know that if this is area 1, and that is 6 feet, what do we know about the moment? We know then that M max is equal to 6 times 600 divided by 2, and we know then that that is 1,800 foot-pounds. Now keep that number in mind, 1,800 foot-pounds. V max is 600 pounds. And we have a good idea. We know that number right there is 1,800. Now make sure you check my math as we go along here. I don't want to get down to the end of this and realize we've made a math mistake. Okay, everybody should be happy here. Now we can take these values and check our bending stress, our shear stress, and we'll look at deflection down the road a little bit. Let's check bending and shear first. Well, we know from our, let me change colors here. We know to check bending, and I'll just put it right here. Let me change colors here. Check our bending. I can't get colors changed here. Let me try that. Oh, let me try again. There we go. We know that our bending stress equation looks like this. Bending stress is equal to, if you'll recall, MC over I, which is equal to the moment divided by the section modulus. All right, well, we know something about each one of those values because we know something about the moment. We know something about the bending stress. Let's do something about checking our section modulus. All right, now as we progress, let us assume, just for sake of discussion, we're going to try a 2x10 member. Now, given that assumption, let's walk through it and check to see what our moment might be, or our section modulus. For a 2x10, we know that the area, we look these up, is equal to 13.88 inches squared. We know that the section modulus about x is equal to 21.39 inches cubed. Remember that. And we know that the moment of inertia with respect to the x-axis is 98.93 inches to the fourth. And then remember, we can look those all up on the charts that I gave you. So let's check it out. So let's look at our bending stress, and we will solve for a section modulus. And let's see here, section modulus, if we solve that, is equal to the moment divided by our bending stress. So that's going to be equal to our 1,800 times 12. Remember, that's to get it into inches. Our allowable bending stress is 1,250, but if you'll recall, we have a repetitive member factor of 1.15, which we can use that against our bending stress because we have numerous members together, because remember it is spaced at 24 inches. So the book says we can bump that bending stress up by 15%. That number turns out to be 15.03 inches cubed. Well, 15.03 is less than 21.39. Therefore, it is okay in bending. Just look back up here. The 21.39 is what we allowed for our 2x10 that we are assuming will work. So far, so good. All right, we've checked bending. So far, bending is okay. Now let's just step down and let's check our shear stress. Well, recall that in shear, please check here. Here's our shear. We recall that shear FV is equal to 3, get the pin right here, 3/2 of V divided by A. All right. Now let's check to see we can solve for our area. Algebraically, our area then is equal to 3/2 over our V max divided by FV, which is therefore equal to, and recall our maximum shear value is 600 pounds, divided by our allowable stress, which is 95 psi, which is equal to 9.47 inches squared. Now, by checking, you'll note that the 2x10 has an area 9.47 is less than our 13.88, therefore okay in shear. So far, so good. Now, we have to check the deflection to see how that might be, because recall that we said for deflection we had to check a couple of things. Well, for our example here, we're just going to check total load. And recall, we'll move over here to get deflection. I need a little room. Again, this is new. We haven't done deflection before. But pretty straightforward. You'll notice from our beam, let me scroll back here. You notice from our beam that it is a uniformly loaded it is a uniformly loaded, simply supported beam. Simply meaning, let me change colors here, that it is uniformly loaded over the span at 100 pounds per foot, and simply supported means it's only supported at the endpoints with those reactions. Now, let's move on just a little bit here, get the screen down and check our deflection. If you look on the tables I gave you, you're going to find that that deflection for a uniformly loaded, simply supported beam looks like 5 W L to the 4th over 84 E I. Okay. Now let's check for total load, and let's solve for I. Because we have an I, let's solve for I with respect to the x-axis. Because we have an I. We have an I for our 2 by 10 of, for a 2 by 10 equals, back up above right here, equals 98.93 inches to the 4th. Now with our loads and our length, let's check to see where we are. So, doing the algebra, let's walk through this a little bit. And I required for our total load then looks like this. We're going to use the I that we're given. And let's see, we look back and that number is 98.93. No, I guess we're going to solve for that. My mistake. We're gonna solve for that. So we're going to solve for the I based on our load. So that looks something like this: 54.89 times 1200 divided by 960 times 240 over 360. That number equals 45.74 inches to the 4th. Now stay with me here. We've got to make one more little check, because we need to know right here, where did this number come from, where did this number come from, and where do those numbers come from, to get to this value right here. Okay? Now we notice that that number is less than 98 point, let me look back up here, 98.93 inches to the 4th. Therefore, deflection is okay. But we have to do one other check. Okay, and we'll do the math right over here on the other side, and it looks much like this. You might remember that we said for deflection we had L over 360 and we had L over 240 from classroom discussion talk. Now, let me back up slightly here Getting used to my new pen. Back up here, we had our total load of 100 pounds per lineal foot. Well, the total load, and I'm going to mark it right here, comes from 40 pounds per square foot dead load and 10 pounds per square foot live load. Now also recall that at 2-foot spacing, we have to multiply, remember, by 2. Therefore, that's where when we multiply that by 2, when we take the 50 times 2 is equal to the 100 pounds per lineal foot. Look back at your notes from when we walked through that in class. You'll remember where that guy right there, and let me star it, came from. It's critical that you remember that this thing is spaced at 2-foot centers, and so that's where those values come from. Now, if you look to see if that's dead load and live load, you'll notice it looks something like this. Our I for then just live load looks like this. We have 5 times 2 times 40. Oh, I just noticed I have these, and let me star those. Sorry, these are turned around. So this guy is live load. This guy down here is dead load. All right, stay with me. All right, there's our 2-foot spacing times 40 pounds per square foot times 12, because we got to get this thing into inches. Okay, remember that. Over 384 times our 1.7, which was our E. Remember that? Look back up above. 1.7 times 10 power 6 times 12 by 12 over 360. Now remember, up above we've got to check, we got to get the units right. And remember we talked about there's a 12 cubed up there for 1728 times another 12 cubed. So we got to get the units right. So a little exercise, if you'll notice, is, let me star these for you. The math here, and please check my math. I'm doing this as we go along here. This number is the 54.89 inches to the 4th. And if you'll recall, I'm going to go back up here. There is that number. Now, what we need to do is, and you notice that number is less than 98.93 inches to the fourth, therefore, okay. Now notice we have checked, let me mark these for you, we've checked the I required for live load, and we have checked the I required for the total load. Now your task is to look at this and check the units in my math. Because remember, we said in the deflection equations you're always going to end up with units that look something like pound, feet cubed, remember that, over inches cubed. And remember, the idea was, when all this is said and done, we want inches. So we have to do some algebra and some unit manipulation here to get that to track. So your exercise would be to go through here, and we'll do this momentarily. Since this is the first time we've used this, we'll go through this momentarily and see from this discussion if you can figure out what these units. Look right here, this is pounds per foot, all right? And this is 12 inches per foot, so this is going to be something that looks like pounds, let me get this pen to right, per inch. And remember now, down here we have pounds per inch squared. Great place to start. And we will we'll end it right there and move on to the next problem, but give that problem some thought. Here is the assignment. Check CHK math and units. Okay, and we'll be interested in your comments to see if you tracked with this okay, and if this thing works, we're going to do some more of them. But let me know how you like it, and we'll try to do some more. So good luck, and check those units in that math.